Good morning to all. It's very happy to welcome our today's session speaker, Dr. Vijaykumar. He has obtained his bachelor degree in electrical and electronics engineering in the year 2006 from Coimbatore Institute of Technology, Coimbatore, and he has completed his MTech degree in power system from National Institute of Technology, Tiruchirappalli in the year 2009 with the MHRD scholarship. Subsequently, he admitted as a PhD research scholar with the MHRD's fellowship in the Department of Electrical and Electronics Engineering, National Institute of Technology, Tiruchirappalli, and he completed his dissertation in the year 2012. He also selected from Canadian Commonwealth Fellowship GSEP at the University of Saskatchewan, Canada, during his PhD. Further, he was a postdoctorate research fellow in Nanyang Technological University, Singapore, from 2012 to 2013. He achieved a POSOCO 2014 awardee from doctoral category and listed his PhD dissertation in the top 10 among the all IITians and NITians in the year 2014. The award is given by Power System Operation Corporation, Power Grid Corporation of India, in sponsorship with Foundation of Innovation and Technological Transfer, IIT Delhi. Dr. Vijaykumar is currently working as a faculty in School of Computer and Electrical Engineering, Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram, Chennai. He was an assistant professor in Department of Electrical Engineering, Malaviya National Institute of Technology, Jaipur, Rajasthan, India, in the year 2013 to 2018. He also holds his adjunct faculty position in National Center for Disaster Mitigation and Management, MNIT, Jaipur. He received Young Scientist Award at Startup Research Grant, which was given by SERB DST in the year 2015. He also a young faculty fellow for Ministry and of Communication and Information Technology since 2016. He was a visiting professor at University of Saskatchewan, Canada, and fellow of Indo-Canadian Swiss 3 Institute. His research interests include design and development of DSP-based power electronics controllers and of power renewable energy, industrial electronics control, smart grid, power electronics and electrical machines, fax controllers, and SMPS for a telecommunication system. All the research work and article of Dr. Vijaykumar are based on the experimental work related to the power engineering. Also, he has a very strong knowledge in fabrication and testing of prototype based power electronics controllers for renewable energy conventional industrial drive system by using digital and analog controllers. He had a hands-on experience in the working with a number of sophisticated equipments and instruments like power quality analyzer, digital signal processing, FPGA and D-space controller, etc. I once again welcome you, sir. I ask him to present the session, sir. Thank you.
Yeah, thank you very much, Mr. Balaji, for give a brief introduction of me. Very good morning to the participants and the coordinators of this program. And I would like to thank the coordinator, Dr. Malathi, for giving the opportunity to deliver the lecture in this workshop. I hope you can able to see my PPTs, right? I already shared with you all.
Yes, sir. It is visible, sir.
Yeah, sure. Thank you.
You present in presentation mode, sir.
Okay, I'll do it. Yeah. So, good morning all. In today's topic, we are going to discuss about various power electronic converters for wind energy conversion system. The topic of today's talk also it's aligned with your workshop theme, impact of power electronics towards green energy technologies. So now just we'll see what is the difference between the green energy technologies and clean energy technologies. So when we talk about the green energy, we can say the renewables like photovoltaic and wind and all is coming to the picture. So when we talk about the clean, this renewable energy sources also is come part of that clean energy sources. In addition to that, the fuel cell and nuclear energy sources also into this clean energy sources. So in broad way, we can say the application of power electronics in clean energy sources. So just we can include the fuel cell and the nuclear power plants also in it. Why? Because we are talking about electric vehicles, hybrid vehicles and all. So in the hybrid vehicles, even people are talking about fuel cell based vehicles. So even when we go into that the power generation point of view, just we are going little towards nuclear power generation and also. So here when we talk about power electronics, so why we need this power electronics? So I turn off my camera. Why? Because I'm going to make my laptop as a tab in the tab mode so that I can able to write it. Are you all right?
Yes, sir.
Yes, sir.
Yes,
It
sir.
is so.
Yeah.
Now
yeah,
it is.
sure. Yeah. Okay. So now when we come into that power electronic controllers for wind energy conversion system, so in wind also we need to use power electronic converters. Not only in the wind, if you talk about photovoltaic systems, if you talk about transportation, electric vehicles, or if you take fuel cell system, any renewable energy systems, or you can say electric vehicles also, it's a kind of application. Any application if you take nowadays, obviously we are using the power electronic converters. So now I put a question to you, why we need this power electronics for the renewable energy application, as well as in the load perspective in electric vehicles, right? So just we will discuss this question after some introduction about this renewable energy sources and all. So please think about it. So energy transformation by 2050. So if you take the energy transformation by 2050, why we are transforming to renewable energy sources? So the main objective of the energy transformation is to reduce the carbon emissions. So even every government, they are planning to reduce the carbon emissions by 70%. Even if you have heard the news, even the China and all, they have cut the export of the commodities like the steel, or we can say the copper and all, to other countries. Why? Because they want to reduce their carbon emission in their country. So that's what they have stopped the export of the steel and copper. So that's what if you can see in the last 6 months, this copper and steel prices have skyrocketed, right? So that's what is a one way of to reduce the reduce the mining activities in their country. In addition to that, in power generation, most of the power generation are from fossil fuels. So once you reduce the fossil fuels like coal or oil, we can able to reduce the carbon emission of the particular country. So that's what even India also, we are focusing on the reduced carbon emissions by reducing the fossil fuels in the power generation stations. And this is the one main objective. Then when we come into the another objective, falling energy cost. So even the best example, you can take the photovoltaic systems. So in a photovoltaic system in a 2009, if you consider, so if you want to buy a panel of 200 watt, is a single panel, right? The single panel capacity is 200 watt. the cost of the panel is around, we can say it's 40,000 rupees, right, in 2009. So do you have any idea about in 2019 or in 20, within a decade, what is the cost of this 200 watt panel? Any rough calculation? So we can able to purchase this 200 watt, a single panel with 10K, 10,000 rupees, right? Yes. So
15,000.
10 to 12,000 rupees, you can able to purchase the single panel. I mean, even it's differed from vendor to vendor, but you can see that the 4 times the cost is reduced. So if you reduce this cost 4 times, then if you are generating the power from the photovoltaic power plants, the cost of the electricity also will go down, right? So even you can check it in the MNRE website, Ministry of New Renewable Energy. So there you can get the bidding cost of the PV and wind energy conversion system. So do you have any idea for 1 unit of energy in how much price they are purchasing? You know the bidding cost of that renewable power? Have you checked in the MNRE websites? Or anyone having the idea about it? Roughly, what is the cost they are purchasing, bidding cost of this solar power or wind power? Yes. So we are talking about the green energy, right? So this is a basic information. So what is the cost of this solar power or renewable power? The yes.
8 rupees per kilowatt hour, sir.
Yeah, kilowatt hour, 1 kilowatt hour. So 1 unit of power. Any idea of what's the cost?
Okay, 7 rupees per kilowatt hour, sir.
7 rupees. It's 2 cost. So the bidding cost of this PV and wind power is 1.9 rupees. You can check it in the MNRE website. Even still it's available. So the government is purchasing for roughly, you can say it's 2 rupees. So even this Gencos are ready to sell this power at 2 rupees. Even the NTPC, Tata Power, Adani Power and all, they are selling their power to that discoms, or you can say discoms at 2 rupees. So the generation of the electricity is the cost of the generating the electricity is reduced drastically. Even this discoms, distributed generation companies, they are selling you for 7 rupees or 8 rupees to the consumers. That depending upon the consumers, whether you are domestic consumers or industries, and depending upon that, the cost will vary, right? So that finally we can say that the electricity generation cost is reduced drastically because of this renewable power generation. At the same time, we can say because of that, we can get the very good economic gain. And at the same time, if we talk about energy security perspective, so in India, most of the power, we can say it's 80% of the power is generated from the fossil fuels. Fossil fuel means we can say it's a coal power generation, or based on the coal or oil as a resources. So this coal and oil we are importing from other countries. So once they stop to export their coal and oil to us, so what will happen? So there is a huge scarcity of this coal and oil, so that the most of the our power plants will shortage with the resources, right? So once, if you think about it, if you are increasing the power generation from the renewable energy sources to 50%, so this 50% from fossil fuel, so the dependency on the fossil fuels will be reduced, so that the energy security of the nation will increase. So that's what, if you can look at it, even in India also, they are promoting the renewable power generation, and the penetration of this renewable power generation also it's increasing, right? So because of that, we can improve our energy security, and at the same point, we can say because of this renewable power generation, we can have the 100% energy access. So how we can say it's a 100% energy access means, if we consider the remote areas or rural areas, so most of the we can say not most, we can say it's only 5% of the locations are away from the distribution network. So in these areas, we can able to go with the standalone power supplies by using this wind energy conversion system or photovoltaic power generation sources. So that's what we can say. We can able to achieve the 100% energy access to the other places also. On top of all these objectives, we can say in a socio-economic perspective, we can able to create the lot of job opportunities for the skilled and unskilled laborers. So that's what the energy transformation by 2050, it's saying that to achieve at least 1/3 of the power generation from the renewable energy sources. So by keeping in mind, in every government, they are working towards to go with the renewable power generation. So this is what we can see here. Even we know that the power generation also is influencing the GDP of the nation. So by looking at the forecasting of the power demand in 2050, almost we need 55,000 terawatt hour per year. So in this demand, almost we can say is the 86% of the power going to coming from the renewable energy sources in 2050. So in this, if you look at it, the total installed capacity, in the total installed capacity, this is PV and this is wind. So wind also 1/3 of the power is going to compensate from the wind, and another 1/3 of the power is going to coming from the photovoltaic power generation sources in 2050. So if you are planning to increasing the installation of this renewable energy sources, then we need a technology also in that case. So when we talk about these resources, wind or PV, we need power electronic converters, right? Power converters are playing a huge role in this power generation. So why we need these power converters? Anyone? When we talk about the wind, PV, or in the demand side, if I mean load side, if you look at it, even EVs also is coming to the picture, whether we can say self-charging EVs or the EVs depending upon the networks and all, it's available. So there also just we are using the power converters. So before going to the EV, so why we need power converters in the wind and photovoltaic systems? Any idea from the participant side? Yes. Why we need power converters? I think the participants also can interact, right, in this session.
For microgrid connectivity, we can need
Microgrid?
Connectivity.
Microgrid, yeah, sure. When we talk about the microgrid, if we are having the loads and this distributed generation sources in that system, we can call it as a microgrid.
Yeah. In case of wind, for keeping frequency and voltage within the range, we need power converter.
Yeah, exactly. So when we talk about, I mean, if you are supplying the power to the loads, then just we are supplying the power from this wind and PV sources. So we cannot directly connect to the loads. If you are directly connected to the loads, what will happen? You cannot able to maintain the voltage and frequency constant for AC loads. So why we cannot maintain the voltage and frequency constant at loads? Because as a consumer, I always prefer to have the voltage and frequency constants. then only my loads will perform effectively. So why in this wind and PV case, why we cannot maintain the voltage and frequency constant?
Because our input is variable.
Exactly. So even if you take the source, any source, we can say it's a PV or wind, good answer. And we are having the load, or you can say it's a grid, right? So here, source, when we talk about the PV and wind, in a PV irradiation, wind velocity, I mean, you can say the wind velocity. So the wind irradiation and wind velocity is not constant always in nature. I mean, it's depending upon the nature, right? So this also it's a variable one. If you take the load, in a load also it's a variable one. Even if you consider your home, so in your home you are having the various loads like lights, refrigerator, air conditioner, or TV, laptop, you are having various loads. So you are not going to switch on all the loads all the time. So whenever you record, you are going to switch on and switch off, right? So the loads also it's a flexible one. So if you take the microgrid, you are having the various loads in the microgrid. So the loads, depending upon the requirement, they will switch on and switch off the loads. So it's not necessary that only this time this loads will be on, this time this loads will be on. So always this loads also it's a variable one. So here the source also it's a variable, load also it's a variable. So to condition this power, conditioning this power, you require the power electronic converter in between the load and source. So this is the case of standalone system. So in a grid connected system, in a grid also just we are having the fluctuations in the grid. So we have to inject the constant voltage, constant frequency to the I mean, if you want to connect your source to the grid, you have to maintain the voltage and frequency constant. So in this case, the power electronic converters plays the very important role in distributed generation, or you can say it's in a renewable power generation. So that's what we are preferring the power electronic converters in this wind and photovoltaic system. So here the power electronic converters means depending upon the nature of the load and nature of the source. So whether the load is AC or DC, if you consider the source also, when we talk about the PV, it's a DC. When we talk about the wind, we are having the electric generators. So when we talk about the electric generators, always it's a polyphase machines. That means 3-phase machines. So it's obviously it's a AC. So just you may use here DC to AC converters, or DC to DC converters and DC to AC converters. And that and also depending upon the design of your system, right? So but here you need power electronic converters between the source and load. So clear? Any clarification on it? Okay. So when we come into this wind energy conversion system, so here we are having the various renewable energy sources, or you can say it's a green energy sources. Here I have chosen the wind energy conversion system. Why? Because when we look into that capacity addition to the existing network, wind is the huge capacity as compared to photovoltaic, even till date. But in another 1 or 2 years, the installed capacity of the PV system going to overcome the wind energy conversion system. But even in the 1980 itself, we are having the commercial wind turbines. So, but if you talk about the photovoltaic system, the commercial high capacity power plants come into the picture in 2000, we can say in 2005 or in the 2010 itself, in between the 2005 and 2010. But in 1990 itself, we are having the commercial wind turbines. Even we can say as compared to photovoltaic systems, in wind, we are having the matured technology. So that's what just we had taken this topic and just we further research. So what are the possibilities to enhance the performance of the wind energy conversion system. So if you look at that roadmap, even the 1982 itself, they are having the 22 kilowatt wind turbine, a single wind turbine capacity. Then in 2001, they have increased the capacity to 1 megawatt. Even they have the 1 megawatt single wind turbine. Then if you look at the 2008, the total installed capacity is 100 gigawatt. So 100 gigawatt of the wind power generation is integrated with the network. So we can see here within 10 years, the installed capacity is increased 5 times. So in 2018, the total installed capacity is around 564 gigawatt. So almost we can say increased 5 times. So this is what within 10 years period of time, just the industry growth is 5 times. Even in 2019, if you look at it, we are having the single turbine capacity of 10 megawatt. So it's an offshore wind turbine. That means on seashore, they have installed this wind turbine 10 megawatt. But commercially, if you look at it, 5 megawatt wind turbines are widely available. So it's a single wind turbine capacity is 5 megawatt. So here, but if you look at in that onshore and all, there are various capacities. It can start from 100 kilowatt to we can say it's a 3 megawatt. So this 5 megawatt preferred for offshore wind turbines. So this 100 to even 100 kilowatt, 500 kilowatt, even 900 kilowatt machines are available in the Coimbatore. I mean, if you go across the Coimbatore and Nagarcoil areas, you can able to find a lot of wind turbines. So their capacity is around 900 kilowatt or some 500 kilowatt machines also it's available, right? So this is the present scenario in wind energy conversion systems. So you can see here some statistics of wind energy conversion system. You can see here the total installed capacity of the wind turbine. So we are having the huge capacity in the onshore wind turbines. So even if you look at in the 2018, just we are having the 542 gigawatt of the power from onshore wind turbines and only 23 gigawatt of the power from the offshore wind turbines. But if you look at here, the progress is good in the offshore wind turbine. So they are going to estimate that in 2030 or in 2050, the progress in the offshore wind turbine is huge as compared to onshore wind turbines. What's the reason why we are going for offshore wind turbines? The main reasons are land cost. So when we talk about land cost in the onshore wind turbine, you have to pay a lot for the lands. But in offshore, you need not to pay for land. So one is this advantage. Another one is you will get the constant wind velocity, or you can say the wind velocity is stable in offshores as compared to onshores. Why? Because just you will get a lot of shading effect because of the buildings or because of the trees and all, so that your wind velocity is not stable in the onshore. But in offshore, you will get the very good wind velocity, the stable wind velocity, so that the power captured by that wind turbines also it's huge. So that's what they prefer to go for offshore wind turbines nowadays. This is what you can see here. Even if you look at that deployment also, so annually they are increasing, drastically increasing the offshore wind turbines. So that's what we can able to see from this statistics. And that's what you can see here. By 2050, they are planning to contribute at least 35%. So 35% means 1/3 of the power is going to generate from the wind turbines, right? Okay, so what's the scenario in India? So if you look at the scenario in India, this information you can even you can look at in the Temenari website. You'll get this information. So here till 2019, the total installed capacity of the renewable energy source is 87 gigawatt. So this one they are planning to increase to 175 gigawatt by 2022 by mixture of wind and photovoltaic systems. So this is the target fixed, set by the MNRE. So when we look at the sector composition means various renewable power sources. So here the wind is almost contributing 37.6 gigawatt of power, and another 34 gigawatt of the power from the photovoltaics. So in a 1 or 2 year period of time, we can say the installed capacity of the PV going to overcome the wind. Almost we can say is 3 gigawatt, right? So within a year we can increase the installed capacity of the PV. And other biopower, other renewable energy sources like biomass, biogas, and small hydro. So in terms of 10% or sorry, not percent, is we can say is a 10 gigawatts. All right. So this is the sector composition of the renewable energy sources in India. Even the government also is coming up with a lot of initiatives like green energy corridor, hybrid policy, solar parks and all are available. So with that they will get a lot of subsidies, and they will get some promotion activities also with these schemes. So when we come into that wind energy conversion system, just we are having two types of wind turbine. One is vertical axis wind turbine and horizontal axis wind turbine. So in a vertical axis wind turbine, you can look at here, the blades are is a vertical. So that's what we can say, it's a vertical axis wind turbine. So in that bottom of the turbine, you are having the electrical generators, gearboxes and everything. So in this vertical axis wind turbine, just we can say it's a high starting torque, but when we come into the mechanical stability perspective, these vertical axis wind turbines are not preferred. So that's what they have moved to vertical axis wind turbines. So in a vertical axis wind turbine, just we are having the tower. On top of the tower, we are having the naturally. So this is called naturally. So in naturally, you are having the generators, gearboxes and everything, and you are having the blades on the hub, right? So this is a horizontal axis wind turbine. So commercially, you can able to see these wind turbines widely in the onshore as well as offshore, right? So here, what are the components available in the wind turbines? Just quickly, we can go through it. So that it will be very easy for you to to justify why we need power electronic converters and what type of power electronic converter topologies we can design for the wind turbines. So without knowing this basic operation and basic components of the wind turbine, it's very tough to design the power converters for standalone application or grid connected systems. So once if you understand the basic operation and their components, it's very easy for us to design any converter or to understand why people are crazy about to design various converter topologies for this wind turbines. Okay. So here I told it this is the naturally. So in a naturally, so what are the components available? So you can see here, this is the hub. In hub, 3 blades are connected here. So these 3 blades will convert the kinetic energy into mechanical energy, right? Converts the kinetic energy from the wind to mechanical energy. So this mechanical energy can be passed to the generator through low speed shaft, because even if you look at the wind turbine may rotate around, we can say it's a 50 RPM to 100 RPM. So this is called low speed shaft. So this low speed shaft connected with the gearbox. So this gearbox convert the low speed to high speed, and that high speed shaft is connected to your electrical machine. So this electrical machine convert the mechanical energy into electrical energy, right? So this gearbox plays a huge role in the wind turbines. Almost we can say 30% of the cost will go into the gearbox, right? 30% of the cost will go into the gearbox. Even in a gearbox, maintenance happen because of this gearbox and the electrical machine, right? Okay, so I'll come to that points later. Now we can discuss only the components. Then here in between your naturally and the tower, you are having the yard drive. So this also is a kind of electrical drive. So why we are using this electrical drive here in between the naturally and tower means, so if you look at the wind direction, so wind direction is constant every time? No, the wind direction will keep on change. So depending upon the wind direction, your naturally can be rotated, whether it should be eastern face or it should be a south face, you can do it. That can be done by the yard drive in the system. So for this yard drive, what is the input you need to give it to the yard drive? So the input to this yard drive is wind direction. So how you will get the wind direction for this yard drive? So that wind direction will be given by the wind van. So this wind van will decide the or you can say is determine the direction of the wind. So then this input will be given to the yard drive. Then the yard drive can rotate your naturally to face the turbine to the wind, right? Okay, this is the wind direction. So here you can see here anemometer. So this anemometer is used to measure the wind speed, all right? So wind speed also it's very important. Why? Because just we have to know whether the wind speed is in the permittable limit or it's in over speed or under speed. So depending upon that, your turbine will be off and on, right? Okay. So for that, anemometer can be used for measuring the wind velocity. Please keep in mind, then we will see with that information, that wind velocity, we can implement the maximum power point tracking and all in the wind turbine. So for that also, you need the wind velocity. So these are the various components in it. So if you talk about the rotor components, so this part, blades and everything, so 20% of the cost it's going to this rotor components. And when we talk about generator components, this gearbox and electrical machines also is coming to the place. So almost 34% of the cost will go into it, and that 34% almost we can say more than 60 to 17% of the cost will go to the gearboxes. So that's what nowadays people are talking about, the gearless or direct wind turbines, direct driven wind turbines. You may hear about it. Even if you look at the pamphlets of the wind companies, you can able to see the gearless wind turbines. So do you have any idea about who are the companies in India they are installing the wind turbines? Any idea?
Suzlon,
yeah,
Inox,
Suzlon, Inox, yeah. Then we can say NAG Micon, Vestas. So Vestas is a very good company.
It's from Denmark. It's from Denmark.
Yeah, Denmark based. And Suzlon is Indian company. They are in, they are struggling with a lot of debts and all. We can okay, we need not to focus much on that. But these are the companies they are in the market to install the wind turbines. Even R Power, Tata Power, they are also having their own wind turbine. Even GE also having their own wind turbines. So these are the companies they are installing the wind turbines. Yes.
Enercon.
Enercon, exactly. Enercon also. Okay. So here when we come into that blades, so here it's very important to know that just from the turbine means mechanic, just blades and all that. So from the blades connected to the hub, and we are getting the power output from the turbine. That means the blades are that's converting the kinetic energy into mechanical energy. So that mechanical power output of the turbine, you can write it in that way. So this is very much important. So whenever you are talking about the wind energy conversion system, this equation is very important. So this is the power output of the wind turbine. So the power output, just I am skipping how you are arriving this equation now. Just we can, it's a very easy way only, because we are talking about the kinetic energy. So from the kinetic energy into power, just we are converting into power. So that's what just we are getting this one. So this power output of the wind turbine is of rho AV cube Cp. So here the rho is air density. So that is depending upon the place where you are installing your turbine. And A is area. So area of the wind turbine. So that depending upon the size of the wind turbine. If you are increasing the size of the wind turbine, the area also will increase, right? Area also will increase. So this is the structure based on the structure of the wind turbine. Then Cp. So the Cp is the power coefficient. So this power coefficient is depending upon the tip speed ratio of the turbine. So again, if you are going in depth into it, the tip speed ratio is the speed of the tip of the blade to the turbine speed. So here the power coefficient, we can say it's some constant value. So this Cp, you can say the maximum value is 0.59 because of the Betz limit. The Cp also depending upon the tip speed ratio and the Betz limit. So finally just we can arrive with some constant. So the maximum value of that Cp is 0.59. So if somebody, they may ask about the conversion efficiency of the wind turbine. Conversion efficiency of the wind turbine. So what is the conversion efficiency of the wind turbine is depending upon the Betz limit. So that's what we can say, that if the conversion efficiency of the wind turbine is 59%. So that's the maximum conversion efficiency. So do you have any idea about the conversion efficiency of the PV panels? This for wind is 59%. So what's the conversion efficiency of the PV panels?
Some about 30%.
Sir.
30% is too high.
10 to 15%, sir.
Yeah, 10 to 15%. We can say it's 18%. So 18% is the conversion efficiency of the photovoltaic panel, right? So this what is the maximum energy you are getting from the wind turbine, right? So this equation will be very useful when you are designing the power converter. So please keep in mind. So of rho AV cube Cp. So the maximum conversion efficiency of the wind turbine is 59%. So these are the information, you can get it from this slide. Okay, now I'll come into the this equation. Now I told you rho is air density, so that is depending upon the place where you are in. Here area of the wind turbine. So area of the wind turbine means we can say this is the turbine. So in the turbine you are having the 3 blades, right? So in the 3 blades, if you are connecting the tip of all these blades, it's a kind of circular. So this is the area of the wind turbine, right? So if I want to increase the power output of the wind turbine, if I want to increase the power output of the wind turbine, so what I need to do with the area? So just if I increase the length of the blade, what will happen? If I increase the length of the blade, what will happen? My area will increase or decrease?
Increase.
Yes? Yeah,
Increase.
area will increase. If area increases, the power output of the wind turbine increases. So for increasing the area of the wind turbine, I have to increase the length of the blades. I have to increase the length of the blades. So this is in the mechanical structure, right? Okay. So another thing, if you look at it, the power output also depending upon the wind velocity. VW is the wind velocity. So if your wind velocity increases one time, so you can see here the PM PM directly proportional to the cube of the wind speed. Cube of the wind speed, sorry, PM, not PP. PM directly proportional to the cube of the wind speed. So even if any change in the wind velocity little, that will give the more impact on the power output of the turbine, because the output of the wind turbine is cube of the wind speed, right? Cube of the wind speed. So that's what any small change in the wind velocity that will give the huge impact on the power output of the wind turbine. So this is wind velocity is not in our hand. That's depending upon the nature, right? So the wind speed increases, then power output also will increase. So these are the parameters influence the output of the wind turbine. So now we'll come into the characteristics of the wind turbines. So that's very much important. So once you understand these characteristics, then you can able to compatible your power electronic converter characteristics with this turbine characteristic. So that's what we have to understand these characteristics. So how we are getting these curves and all, I'll explain to you. So that will be very easy. Yes. That will be very easy for you to understand. So we can look at here. Just we know PM equal to half rho AVQ into CP, right? So with this, what you can do is you can vary the wind velocity. You can vary the wind velocity, or in this case you can see here for one wind velocity point, I'll fix the wind velocity as 0.5. I'll take all units in per unit systems. So for 0.5, wind velocity, I'll fix it here. Then you can CP is depending upon the tip speed ratio and the Betz limit. The Betz limit is constant, and you can vary the speed of the wind turbine. You can vary the speed of the wind turbine, and rho also, air density also you can keep it constant, and A also, so varying the speed of the wind turbine, and you can plot the power output of the curve. So for one wind velocity, for example, for 0.9 wind velocity, you will get this curve. For 0.5 wind velocity, you will get this curve. For one per unit wind velocity, you will get this curve. So for each and every wind velocity, you can plot the curve, right? Then you can look at here. I'll take an example of this one per unit wind velocity. In a 1 per unit wind velocity, this is the curve, right? So this is the power output of the turbine. Power output of the turbine in y-axis, and the x-axis you are having the speed of the turbine. So here you can look at here. So if I'm operating my if I'm having the wind velocity 1 per unit, at that time, if I'm operating my wind turbine at this location or at this speed, I can say the wind turbine speed is 1.2. So what's my power output of the wind turbine? The power output of the wind turbine is, I can say it's a 0.9, right? 0.9. So instead of operating my wind turbine at this speed, I can operate my wind turbine at this point. So at this point, my wind turbine speed is 0.8, I can say. In the 0.8 also, my power output is 0.9. So this is the optimal point to operate my wind turbine? No. So the best point is this one. If I'm operating my turbine at 1 per unit, I can get the power output from the turbine is 1 per unit. So which one is higher, 0.9 or 1? So 1 is the higher side. So which point I prefer to operate my wind turbine at wind velocity of 1 per unit? So this is the point. So at that point, I have to make sure that my turbine is rotating at 1 per unit. 1 per unit. So if I'm ensuring my turbine operating at 1 per unit, the output of the turbine is 1 per unit of output power, right? So this is the optimal point to operate my wind turbine, the wind velocity per unit. Am I right? So indirectly what you are doing, you have to ensure the turbine speed at 1 per unit, right? So for my wind velocity is 0.9 per unit. So that time I have to ensure that my turbine is rotating at 0.99 per unit. Then only I'll get the optimum point. So for each case, if you look at it, for each case, something. Okay, at each case, at each wind velocity, you can see here you have to ensure that you have to operate at the optimum speeds, right? If my wind velocity is 1 per unit, I have to ensure my wind turbine speed is 1 per unit. If my wind velocity is 0.9 per unit, I have to ensure that my turbine speed is 0.9 per unit. So just you have to adjust the speed of the turbine. You have to adjust the speed of the turbine to implement the maximum power point tracking. Because in real time, my wind velocity will keep on change. It's not a constant speed. So in every time, my wind velocity will keep on change. So once your wind velocity changes, your optimal point also will change. So accordingly, your speed of the wind turbine also need to be changed. Then only you can able to implement the maximum power point tracking in the wind turbines. So for that, you have to control the speed of the wind turbine. So now the question will come to you, how we can control the speed of the wind turbine. So you can tell me now how you can control I have to control the speed of the wind turbine. So how I can control the speed of the wind turbine?
By using gear mechanics.
Gear, with a gear we cannot control it, because if you talk about the gearboxes in the bike, you are changing the gears. I mean, you are having the 4 gears and changing the gears, and you are changing the speed of the vehicle. But in a wind turbine, just we are having the fixed fixed number of gearbox stages in that. So we cannot, I mean, in the wind turbine we cannot change this gearbox, or gearbox stages. So gearbox is fixed.
So we can make the larger weight of wind blades.
Yeah, not wind blades. That also, it's in a real time, you can think of it in real time. The wind turbine is installed. The blades also is fixed. The gearbox also is fixed.
Yes.
So how we can do it? And the weight of, if you are increasing the weight, again, the structure will be collapsed. I'm right?
Yeah. Yes.
By changing the direction of blades.
Through circuits, power electronic circuits.
Power electronics, how? So I'll going back to that. Now I'll take this part now. Now you can tell me how you can change the speed of the wind turbine. Speed of the wind turbine means this part, right? So if I need to change the speed of this part, so how will you change the speed of this part?
By adjusting the pitch, sir.
Yeah, pitch. So that's what you can see here. The pitch means changing the angle of the blades. For example, in your just you are having the ceiling fan in your home, right? If you look at the ceiling fan of your home, the blades are not flat. If just we can notice that the blades are tilted, right? So then only just we can change the aerodynamics of the system. So here also, by changing the pitch angle of the blade, we can able to change the aerodynamics of the system. So that if you're changing the angle of the blades, these 3 blades, if you're changing the angle of these 3 blades, the energy captured by the wind turbine will change, so that the speed of the turbine also will change. So you can see here, we are having the larger wind turbines. So the weight of the each blade also in tons, in terms of tons. So is it easy to do that kind of pitch angle? It's, earlier they have done the pitch control for controlling the speed of the wind turbine. So here the inertia is more inertia is more, so the response time also more. Because of the inertia, the response time also it's more, right? So this type of control, they will say it's a mechanical control, mechanical MPPT. Even in a PV also, earlier they have changed the angle of the panels, right? So they have used the stepper motors on that structure, and they have rotated east and I mean, we can say it's the east or west, or we can say it's the north and south side. That's what they have done. So that also is a mechanical control, right? So here now we are going to electrical control. So in electrical control, you can see here this shaft is connected to your turbine through the gearbox. So here if you are controlling the speed of the machine, you can change the speed of the machine. So if you are changing the speed of the machine, you can able to control the speed of the turbine. If you are controlling the speed of the machine, you can able to control the speed of the turbine. So how you can change the speed of the machine? How you can change the speed of the machine?
By using differential component generators.
Generators, how? The generator is fixed, whether it's induction machine or permanent magnet machine or any kind of machine. Machine is fixed. So how will you control the speed of the machine?
120 F by P, sir.
Yeah, 120 F by P. That's a machine,
Flux
right?
control.
For if you are saying it's an induction machine, you can say changing the frequency. So how will you change the frequency? Or pole changing and all, it's a old techniques. Even if you are changing the poles in the machine, then you need to take out of the windings of the machine and you have to do it. But wind turbines are located in the remote locations. If you are taking the windings out and if you are playing with that, then you need huge maintenance things, and even you need a skilled labors for that. But I need the robust system for that. So pole changing also it's not possible. Then
By adding rotor resistance.
water resistance, we can say, I mean, I told you 120, you say it's a 120 F by P, right? So pole changing is not feasible. So that's what just we are leaving it. Then what is the another option? To change the frequency. To change the frequency F. So how will you change the frequency F in the machine? This machine is connected to your power supply, right? I can say power supply, or you can say it's a grid or load. So how will you change the frequency?
Using cycloconverters.
Yeah, that you can say is the cycloconverters or any inverter. So that's what the power electronic converters come into the picture. Power electronic converters come into the picture. So by using these power electronic converters, you can play with the voltage, frequency and everything, so that you can able to change the characteristics of the machine, so that even this grid you are getting the constant voltage and frequency. So by using the power electronic converter, you can able to change the voltage and frequency. So that's what in your electrical drive subject you have studied the V by F control, vector control, right? So these control strategies can be used.
Phase
So,
control.
sorry?
Phase control, sir.
Phase control. V by F, that's a scalar control, right? So a vector control is a field oriented control. They will say it's a vector control is a field oriented control. So by using these control strategies, once you are very good at the electrical drives, then the same technique you can use it here for implementing the maximum power point tracking. So what's the maximum power point tracking? You have to control the speed of the turbine. For controlling the speed of the turbine, just we can play with the speed of the electrical machine. So for playing with the speed of the machine, you need the power electronic converter technologies. So with that, we can, whether we can go with the inverter fed machine or cyclo converter, or you can go with any converters, then you can able to control the speed of the machine. So once you control the speed of the machine, then the speed of the turbine will change, so that you can able to achieve the maximum power points. You can able to achieve the maximum power points. Then you can say your system is operating in the maximum power point tracking mode, right? So just you can, I mean, connect all these points so that you will get this area of the curve. So here you can see here, that's what they are mentioning, that in this area you are doing the generator control. You are doing the generator control. So whenever you are implementing the maximum power point tracking algorithms, the area in that characteristics is this one. So in this area only you will do the maximum power point tracking algorithms, right? Okay. So here this is the normally when we talk, this is the characteristics, and this one they will say it's a power curve of the wind turbine. So in the power curve of the wind turbine, you can see here cutting speed. Normally the generator start to operate in the cutting speed. So below cutting speed, they never operate the machine. Why? Because if you are operating the machine below cutting speed, the whatever the losses in the machine, that is enough for generated power. So there is no use to operate below cutting speed. So above cutting speed also, the power generated from the wind turbine is more than your system losses, so that power can be fed into the grid or supplied to the loops. So that's what cutting speed. Normally cutting speed will be 3 to 5 meter per second wind velocity. Then you are having the rated speed. So in the rated speed, if you can see here, the rated speed is 15 meter per second. It's a typical, even depending upon the turbine, these numbers also change, not much. We can say plus or minus 2 or 3. So in a 15 meter per second is the rated speed, and the rated speed you will get the rated power of the wind turbine. So if I say 1 megawatt of the turbine, right? 1 megawatt of the turbine at rated speed, I'll get the 1 megawatt output. So after rated speed, whatever the speed, you can see here, whatever the speed, the power output of the turbine is 1 megawatt. So it's not going to increase. So the rated power speed itself, we are getting the rated power output. So after that, whatever the wind velocity, your output power is 1 megawatt. So here you need not to do any kind of maximum power point tracking. Only you have to implement the maximum power point tracking from cutting speed to rated speed. After rated speed, your power output of the turbine is constant. So up to cutout speed, you can able to operate the turbine. The typical cutout speed of the wind turbine is 22 to 25 meter per second, right? So up to that, you can able to operate your turbine. So after cutout speed, you have to stall. You have to stop. You can say it's the stall or stop the wind turbine. Why? Because afterwards, if you are operating the turbine, it leads to damage your turbine during the gusty wind speed. Gusty wind means whenever you are having the cyclones and all, that time just the wind velocity is more than 22 meter per second or 25 meter per second. That time you have to stall the wind turbine. For stalling the wind turbine and controlling the speed of the turbine in that after rated wind velocity, normally they will use the stall and pitch control. They're changing the pitch angle of the blades, and they will control the speed of the wind turbine. For implementing the maximum power point tracking algorithm, just they will use the generator control. So generator control means they will use the electrical control by using the power electronic converters. That will be in the cutting speed to rated speed. So this is the basic characteristics of the wind turbine. So once you know the basic characteristics of the wind turbine, you know, it will be very easy for you to design the control strategies for your power electronic converters. Otherwise, it's very tough. So you will be confused that why we are using this, why they are using this control this in this region and all. It will be very tough to understand. So once you understand this various operating regions of this wind turbine characteristics, then it will be very easy for you to design and implement the control strategies. So whatever, not only in the wind turbines, even if you take any application for EV or fuel cell technologies, first you have to understand the characteristics of the source or characteristics of the load. Then only you can come up with your control strategies. So what control you need to do, and what are the regions, and what are the different operating modes, and all. If you know, then that will be easy for you to design the control strategies, right? So for wind energy conversion system, you must understand these characteristics, then only you can able to design the proper control strategy, right? So any clarifications or any doubt on this characteristics, I will be happy to answer to you, so that it will be very easy for you to understand the coming slides. Not only coming slides, just it will be very easy for you to design the controllers.
It's clear, sir.
Yeah, thank you. So when we come into the wind energy conversion system, you are having the two types. One is grid connected system and standalone system. So in a grid connected system, whatever the power you are generating from the wind turbine, you have to inject into the grid. So when you are injecting into the grid, what are the conditions? Just you have to take care of it. Any idea? I think most of you from electrical engineering background, right?
Yes, sir. Yes, sir.
Sure.
Voltage, frequency, phase sequence.
Yeah. First one is synchronization. That's what we can say. It's a synchronization. For synchronization, voltage, frequency, and we have to take the phase sequence, right? Phase sequence. So these things you have to take care of it, and you have to synchronize with the grid, right? So that's what already we have discussed. The power electronic converters are available. So the power electronic converters will take care of the synchronization, right? Okay. What are the control parameters I have to maintain? Even if you are having the inverters or power electronic converters, one is you can implement the maximum power point tracking, right? Maximum power point tracking incorporated. But what are the control parameters? When you are connecting to the grid, people will talk about the power control. Power control means independent real and reactive power control. So independent real and reactive power control, that means if you want to operate your wind turbine with the unity power factor, just you have to maintain the Q. So whatever the Q required for your wind turbine, that Q can be supplied. I mean, Q means it's a reactive power. So that reactive power can be supplied by the inverter, right? Okay. So this is the independent controller. Even you can take any papers in a research, in IEEE transactions, or in elsewhere, or I mean in any research paper, when they are talking about the grid connected systems, in control perspective, they will discuss about the independent control of real and reactive power. So this is the one area they will work on it. Then another area, they will implement the various maximum power point tracking algorithms for the grid connected systems. So in this grid connected system, you can say it's a wind or photovoltaic. For photovoltaic also the same thing. So they will implement the various MPPT techniques. Then some people, they will work on the synchronization. So synchronization, we are saying, so we have taken care of voltage, frequency, phase sequence. So this and all you can achieve by using the PLLs. We can able to achieve by using PLLs in the controller of your converter. So people, they are doing the research on phase lock loops. So especially phase lock loops, people are working. So we can, the system is saying, we can design, I mean, we can design the various phase lock loops for the grid connected system. So people are working on it. Or we can take the same system, grid connected system, or machines are same, then we can use the various MPPT algorithms, right? Same system, different algorithms. And systems are same, they will work on independent control of P and Q. And few people, they will work on the power converters, power electronic converter topologies. So they will design the various topologies for grid connected wind system or grid connected PV system. For example, for various power electronic converter topologies means in between your panel and your grid, you can have the diode, DC to DC converter and inverter. Some people, they will eliminate this DC to DC converter and inverter with matrix converter, or we can say some people, they may work the same DC to DC converter and inverter topology. People work on different DC to DC converter topologies, even buck converter, boost converter, cut converter, SEPIC converter. Just we can say it's in your own converter you can design, even quadratic boost converters and the people are working. So some people, they will concentrate only on power converter topology side. The controller, they will same control, existing control, they will take it, and they will design the different converter topologies, right? So these are the various research areas when we come into the grid connected system. So in control perspective, in grid connected system, you have to control the real and reactive power. Okay. Now I'm coming to the standalone system. So in a standalone system, what other areas you can work? Anyone having any idea about it? Standalone. First, what is standalone systems or isolated systems? So here you are generating the power and you are injecting the power into the grid. Here in a standalone system, as its name implies that just you are generating the power and you are supplying your own loads, maybe the one load or with the different loads. For example, microgrid systems. So I'm generating the power from the photovoltaic system and I'm supplying to my home. So there is a standalone system. I'm not connecting my home to any network, right? So what are the control parameters I have to take care here? As a consumer, I'm having the load. I'm having the lights and refrigerators, air conditioners. So what's my expectation from the supplier? I have to maintain the voltage and frequency constants, right? So for AC loads, I need to get the constant voltage, constant frequency. For single phase, 230 volt, 50 hertz. For three phase, just you can say it's 415 volt, 50 hertz, right? So I have to maintain the voltage and frequency constant. So that's what in a control perspective, people work on maintaining the constant voltage and frequency at the load side, right? Even you can take any standalone system paper, whether it's a wind or photovoltaic or hybrid system, people work on this perspective. Okay, so here in a standalone system, I already told you, just we are having the source wind or PV, we are having the load, right? Load. This wind PV also will keep on change, load also will keep on change. You never ever come into the PV equal to load. So what will happen if you are not coming this condition, PV equal to, that means PV means whatever the input power you are having, the input power never matches with the load, right? So what will happen if even if your PV greater than load, PV greater than load, then this V by F is possible, right? Because your source is more than that, so you can able to maintain the voltage and frequency constant, because you can able to control the supply to the load, because you are having more resource. But when the PV equal to load also, you can able to maintain the voltage and frequency constant, but it's very rare to get this condition. If your PV less than load, if your PV less than load, is it possible to maintain the voltage and frequency constant? Even the load is greater than, but you are having the very less source. So it's not possible to maintain the voltage frequency constant. So what's the solution for it?
We should use some boosters.
No, boosters, no, it's never. You cannot able to able to come with the energy balance, or you can say it's a power balance. If your power balance is not happening, if your resource is more than the load, then you can able to maintain the voltage and frequency constant. Or if your load is equal to that source, then that time also it's equal. I mean, you can able to maintain the voltage and frequency constant. But PV resource is less than load. Are you getting my point? So even just you are having a, I mean, you can able to generate the 2 kilowatt power from your photovoltaic system. But in my home, I'm having the 5 kilowatt. So is it possible to maintain that voltage and frequency?
No, sir.
It's not possible. Then what's the solution? Yes, anyone? Already known, very known solution.
We need to convert it into AC and then step up with the step up transformer.
No. Here, energy storage devices. Just you can use the battery, right? You can use the battery. Here, I'm talking about the energy balance, power balance, right? So for that, we have to use the energy storage systems. So that case, once you are having the energy storage, or you can say it's a battery, whenever you are having the deficient power, that time just you can able to supply from your storage. Whenever you are having the source is more, that time you can charge your batteries, right? It's very simple technology. So here, once you are coming to the energy storage systems into that, then people working on the sizing of the system. This is what they will work on, sizing of the system. So how you can size your panel or wind energy conversion system, how much of load you can able to supply. So what is the storage capacity required, this and all, you can do it by doing the sizing of the system. So some people they are working on this area, sizing, and energy management EMS, they will say it's a EMS, energy management system. People are working on it, right? Then I mean, if your load is RL load or R load, it's okay. Again, in your home, you are using a lot of adapters, chargers, right? Even your TV also has come up with the SMPS, right? So in that case, you are injecting the harmonics to that. So people are working on the power quality aspects. So these are the research areas you can work on the standalone systems. So in a grid connected system, you have the certain areas. In standalone system, you have the certain areas, right? Okay. So these are the various components of the wind energy conversion system. We already discussed. Just in the when we talk about the mechanical parts, just we are having the rotor, gearboxes, and generator. So rotor, you can able to control. You can implement the pitch control and all, right? So that's what we are saying, power conversion and control, right? Then you are using the gearbox. So gearbox is only for transmitting the mechanical power from turbine to generator, right? So because of this cost, people are now working on gearless wind turbine. I already told you, so that's what I put here as a gearbox as optional. So for gearless wind turbine, PMSG machines, permanent magnet synchronous generators, are the best candidate. So without gearbox, you can directly connect your turbine to the generator, so that the PMSG can able to generate the power at the lowest speeds, right? So why we are using the gearbox here means, what's the reason to use the gearbox here? Anyone having any idea? Because the turbine speed is low. I told you 50 RPM. For example, if you are using the four pole machine and your grid frequency is 50 hertz. So for 4-pole 50 hertz machine, the synchronous speed is, sorry,
1500 RPM. That's why we need
1500 RPM. So to match the 50 RPM with the 1500 RPM of the machine, so when you are if you want to make your induction machine as a generator, you have to operate that machine above 1500 RPM. So above 1500 RPM, this generator will operate. So to match this 50 RPM speed with this 1500 RPM, you need to use the gearbox. All right. So for that purpose, you have to use the gearbox here. Then generator. So and power converters. Generator can convert the power, and by using the controlling the speed of the machine, you can able to control the system. So that's what we can say power conversion control. Again, the converters are used for conditioning. So here also it's optional. I'll tell you. Earlier they have the fixed speed wind turbines. Without turbine, without power electronic converters, they have connected the turbine directly to the grid. So that's what here. But in the modern wind turbines means variable speed wind turbines. Nowadays they are coming up with the power converters. So once if you are talking about the maximum power point tracking, then you have to use the converters. Without converters, it's not possible to implement the maximum power point tracking. Right? Earlier days they have used the fixed speed wind turbines. In the fixed speed wind turbines, they haven't used any MPPT algorithms. Okay. The next is power transformer. Why we are using this power transformer here? This power transformer can be used to match the voltage of the source and grid. If I say my grid is 11 kV, my generator is 415 volt, right? So to match this voltage, then I have to use the transformers, right? Okay, one is to matching the voltage. So what is the other application of the transformers, power transformers? Any idea? What is the use of another application of power transformers? Yes? Isolation, right? Isolation. So because of this isolation, I mean, just is a magnetically coupled, so not electrically coupled. So if it's a magnetically coupled, if any fault in the grid, that won't affect your grid that much, or if any fault in your wind turbine, that won't pass into your grid. So this will provide
voltage, sir.
Sorry, this will provide the isolation. Okay. So next wind turbine concept, I already told you, just we are having the two types of wind turbine, fixed speed wind turbine and variable speed wind turbine. So this wind turbine classification I'm doing with respect to of the wind turbine. So there we have studied the vertical axis and horizontal axis. Here just we are having the fixed speed and variable speed wind turbine. So this is the earlier wind turbine, fixed speed wind turbine. So MPPTs are not available. MPPTs are not available.
The voltage, sir.
Sorry? Yes? Okay, so MPPT is not available. So here MPPT is not available means you need not to use any power electronic converters. So power electronic converters also it's not available. So because of that, I mean, if you're not having the MPPT, then the energy output from the turbine is limited, right? So here it operates at the constant, I mean, it's not exactly constant speed. Here they will use the induction machine. That's what I can see here, school cage induction machines. They will use it as a generator. So school cage induction machines, what is the slip range? You can say 2 to 20% is the slip range. So for a small machine, the slip range may be 20%. For larger machines, the slip range will be coming to 2 to 5%. So only in the 2 to 5% of the slip range, these machines will work as generator here, right? So that's what earlier days, even if you go into any wind farm, 80% of the wind turbines are based on the fixed speed wind turbines. They are not using a power electronic converters. So whatever the wind turbines coming to the market after 2010, they are coming up with the variable speed wind turbine concept. That means with the power electronic converters. So before 2010, whatever the wind turbines they have installed the fixed speed wind turbine without MPPT and without power electronic converters. So here, but that's what these variable speed wind turbines are called, modern wind turbines. So in the modern wind turbines, you are having the power electronic converters. So by controlling the power electronic converters, you can able to change the speed of the machines. So if you are changing the speed of the machines, so it is possible to incorporate the maximum power point tracking algorithms into this wind turbines. So once you are incorporating this maximum power point tracking algorithms into it, you can able to increase the energy captured by the wind turbine, so that you can able to increase the energy output of the wind turbine. So if you are calculating the energy for a whole year, the energy generation by these variable speed wind turbines are higher than the fixed speed wind turbines. So that's what nowadays we are preferring to use the variable speed wind turbines with maximum power point tracking algorithm. So within 2 to 3 year period of time, you can able to get your money back, money back in the variable speed wind turbines. So here you are using the power electronic converters. The power electronic converters cost will be compensated within 2 to 3 years. So afterwards, I mean, we can say normally they will come with the 20 to 25 years of lifetime. So afterwards, whatever the money you are getting, that is the extra profit for you. So that's what they are preferring to go with the variable speed wind turbines. So in the variable speed wind turbines, people are using the PMSG, permanent magnet synchronous generators, W-field induction generators, and wound rotor induction generators. So in these two cases, they are using the slip ring induction machines. The machine is same, but depending upon the converter topologies, they are classifying as WRIG and DFIG. But the machine employed in these two, DFIG and WRIG, are slip ring induction machines. Right? Okay, so first we will discuss about the fixed speed wind turbines. Why? Because in 80% of the wind turbines in India are fixed speed wind turbines. So that's what just we have to get to know that. So that's what I'm explaining here. So here in a fixed speed wind turbines, we never ever use synchronous machines. So why we are not using synchronous machines means there are three reasons. One is, if you want to make this synchronous machine as a generator, even in our lab also we have done the experiment on it. So if you want to get the 50 hertz output, exactly for, if you take, say it's a 4-pole machine, exactly you have to rotate at 1500 RPM, right? So if you are operating at 1505 RPM also, then the frequency will change. So this will create a lot of issues in the system. So you cannot, wind is a variable one, so you cannot able to operate exactly 1500 RPM. So that's what these synchronous machines are not preferred for the wind turbines. Then another reason, just here if you're talking about the school cage machine, is a singly excited. Singly excited means just in a induction machine, school cage machine, in a rotor we are having the copper bars that will be sorted, and only you can able to access the stator windings. So only that's what we can say is a singly fed machine. But if you talk about the synchronous machines, you are having the field as well as armature. So there are two, we can say it's a doubly excited machine. So for field, you need to give the DC, and in armature, you will get a AC. So you require the two types of power supplies. But here only AC, right? Here only AC. So this is another disadvantage. Then if you talk about this synchronous machines, the cost is higher than the school cage machines, right? So because of these three reasons, we will not prefer the synchronous. Even if you leave the cost also, technically it's not feasible to make the synchronous machine as a generator in the wind turbine. So the best candidate is school cage machine and rugged construction. Rugged construction means you need not to require much maintenance for the school cage machines, because wind turbines are located in the remote areas, and synchronization not required. So you need not to require any special equipment to synchronize with the grid. Once you connect it to the grid, it will act as a motor. It will act as a motor up to 1500 RPM. So when your turbine is rotating this machine in the same direction above 1500 RPM, it will act as a generator, right? It will act as a generator. So you need not to require any synchronization. and single fed machines. Only starter coils are available to access. And another only main disadvantage of this spool cage machines are lagging power factor operation. Whether it will act as a motor or it's a generator, it's always takes the reactive power from the grid. So always takes the reactive power from the grid. So if you consider that the point of common coupling, the power factor is lagging. Power factor is lagging. So that's a main disadvantage of this generator. This disadvantage also we can eliminate by connecting the capacitor banks at the point of common coupling, so that reactive power requirement of the machine will be provided these capacitors, so that at the point of common coupling we can able to maintain the unity power factor. There are a lot of calculations are available to select this capacitor banks. Even nowadays people are working on StatCom at the point of common coupling, so that you will get the smooth reactive power compensation to the machines, right? So the people are working on it. So this is the fixed speed turbine concept. So this and all, it's a grid connected. So if you are going for a standalone system, I already told you, if you want to make your induction machine as a generator, you need to provide the reactive power. So if you want to supply the standalone loads, then you need to connect the capacitor banks at the starter terminals. Then only the machine will be excited and supply the loads. If you are not connecting the capacitor banks, then it will not work as a generator. So the excitation capacitor is very important in the self for supplying the standalone loads by the induction machines. Otherwise, it will not operate. But the disadvantage with this self-excited induction generator is the voltage and frequency. If I'm connecting the standalone load, I'll expect the constant voltage and constant frequency. But here you cannot able to maintain the constant voltage and frequency. Why? Because wind also it's variable one, the load also it's a variable one. So you cannot able to maintain the voltage and frequency constant. So here in this system, the voltage and frequency depending upon this all four parameters, speed of the machine, the value of the capacitor, depending on the load, and generator parameter. Even generator parameter also it's not changed. We can say it's a constant, but these three parameters plays a huge role with the voltage and frequency of the system. So here if you vary one, the others also will be varying on time. So that's what we cannot able to maintain the voltage and frequency constant here. So what you can do is you can connect some power electronic converter with some energy storage, PE with battery here, and you can have another converter here, so that you can able to maintain the voltage and frequency constant here. But you should use the capacitor banks here, because these capacitor banks will provide the reactive power support to the machine. So when we come into the variable speed generators, there are 4 different types of topologies. Just I'll explain to you one by one. When we come into that variable speed wind turbines, excuse me, when we come into the variable speed wind turbines, there are 4 different types of electrical generators are there. I'll tell you what are the electrical machines you are using and what is the difference between these topologies. So first I'll take the permanent magnet machine. So in the permanent magnet machine, just we can say I'm having a 1 megawatt machine. So 1 megawatt machine I have to connect to the grid. So whenever you are talking about the grid connected system, you need to use the power converters. So these power converters, what can do is, depending upon the wind velocity, you will get the variable voltage and variable frequency. So this variable voltage, variable frequency can be converted into DC. This is the, you are having the machine here, you will get the AC. So we are converting the AC to DC. So we are converting the AC to DC. So you will get the variable DC voltage. You will get the variable DC voltage at the DC link. So this variable voltage we can convert into fixed voltage, fixed frequency, 50 Hertz, 415 volt. So that can be done by inverter, DC to AC inverter. Then you can connect to the grid, or you can say synchronize to the grid. So in the PWM converter, you are having the the control strategy, you have to go with the PLLs and all, PLL, and this converter can taken care of the real and reactive power, PQ, real and reactive power control of the grid. Okay, so these are the parameters, these are the control actions you have to do it in the control of this inverter. This is the grid side inverter. Normally people used to say that this is a grid side inverter. Then you are having the machine side converter. In the machine side converter, just you are having the rectifier. So this converts the AC to DC. So what are the control actions you have to do? You have to implement the MPPT, maximum power point tracking algorithms. At the same time, you are controlling the speed of, indirectly you are controlling the speed of the machine. So MPPT control technique they will implement with this control of this converter, right? So here just you are controlling the speed of the machine, and here you are controlling the grid parameters, right? Okay. So now if you are talking about the synchronization, P and Q control and all, it's possible with this entire topology. That's what this points will tell you. And here when we come into this ratings, so if my machine rating is 1 megawatt, so this all 1 megawatt of the power can be channeled through this converter to the grid. So the rating of this rectifier also, the rating of the rectifier also 1 MVA, because I have to channel all this 1 megawatt to this converter only, right? So I have to use 1 MVA, and this converter rating also 1 MVA. So I can say that the converter ratings, whatever the converter ratings I'm using here, that is almost equal to the machine rating, right? So that's what I can say, full rated power electronic converter. So whatever the converter rating I'm using, that converter ratings are equal to my machine rating, right? Okay. So when we come into the spool cage machines, so instead of PMSG, you are using the spool cage machine. The topology, control and everything same. So the grid side inverter will take care of the P and Q, and it will take care of the synchronization. Then this converter will take care of the MPPT, that means machine side converter, because it's near to machine. So that's what people used to say, that machine side converter. Here it's connected to the grid, so that's why it's a grid side converter. The machine side converter can take care of the maximum power point tracking algorithms, right? Okay. Here already we have discussed about the operation of the spool cage induction generator. For spool cage induction generator, you need to supply the reactive power to make this machine as a generator. So here, if I'm using the PWM rectifier, it's fine because it's a back, we can say normally they will say it's a back-to-back converters. So the both are bidirectional property. Both the converters having the bidirectional properties. So the reactive power required by this machine will be supplied by this converter, right? Supplied by this converter, so that it will act as a generator. So instead of PWM rectifier, what I can do is I'm using the diode bridge rectifier, DBD, diode bridge rectifier. So if I'm using the diode bridge rectifier here, whether this topology will work, instead of PWM rectifier, I'm using the diode bridge rectifier. So whether this will work as a generator, anyone? So if you're talking about the diode bridge rectifier, it's a unidirectional converter. So you cannot it won't pass the supply from this side to this, only unidirectional. So this will not act as a generator. So for that purpose, you need to connect the capacitor banks. You need to connect the capacitor banks at this point. So then if you are using the diode bridge rectifier, then it will work as a generator. So that's what I'm saying. Once you know these basics of the machines as well as converters, then it will be very easy for you to design the various converter topologies for your wind energy conversion system, right? Otherwise it's very difficult. So this on this point you have to know, then only you can able to design the converter. So instead of that, this PWM rectifier, if you are putting a diode bridge rectifier, then you will say, so the machine is not tracked as a generator, means there is no meaning of it. So once you know this point, then it will be very easy for you to design this converter topologies. Okay, now when we come into this same topology, the PWM converter is here. So this will supply the reactive power requirement of this machine, and as well as if I say it's a 1 megawatt, then 1 megawatt of real power it will supply to this converter itself. So here the converter rating, if I'm saying it's a 1 megawatt machine rating, then I have to use 120% of the rating of the converters in the topology. That means if I'm saying it's a 1 megawatt, then I have to use 1.1 MVA, 1.1, or we can say 1.2 MVA rating of the converter. Why? Because the reactive power requirement of the machine, as well as if you want to manage the unity power factor at the point of common coupling, this machine, this converter also can supply the reactive power in addition to the real power. So that time the converter ratings are more than the machine rating in the school cage induction machines, right? So all the other properties also is possible here. That means real and reactive power control, synchronization, everything is possible. But here the converter ratings are more than the machine rating. So in these two topologies, we have discussed the in terms of converter ratings, right? Okay, now when we come into the wound rotor induction generators and doubly fed induction generators. So in a wound rotor induction generators and doubly fed induction generators, normally we will use the slip ring induction machines. Slip ring induction machines. Okay, so in the slip ring induction machines, you can able to access the rotor windings. So in the rotor windings, you are connecting the converters. Stator is connected to the grid. So in the rotor, suppose I'm saying I'm operating this machine at rated power, rated condition. So what is my power at rotor terminals? Anyone? So I can say my stator power is PS. So what is my PR? Anyone? If my stator power is PS, what is my rotor power?
वजह से नहीं, कोरोना तो उसे 1 महीने पहले हुआ था, वो तो ठीक भी हो गया है.
हाँ जी. So your rotor power is slip times of your stator power. So you'll get the slip power at the rotor. So slip power, I can say my machine is operating at 20% slip range. So if I say it's a 1 MVA, I can say only 20 kVA, 200 kVA or 200 kilowatt is maximum available in the rotor terminals. So what is my converter rating? If I'm using 1 MVA, then what is my converter rating? 20%, because I'm using I'm operating at 20% slip range. So you can use 200 kVA, 200 kVA. So you get, that's the max. I mean that's a converter rating required at the rotor terminals. So the converter ratings are less than the machine rating. So even if you are reducing the 10% of the converter rating, that is a huge saving in the system cost. So that is the advantage we are having with the wound rotor induction generators. So in the wound rotor induction generator, we are using the diode rectifier chopper. So here uncontrolled switches. So you need not to give any pulses to the diode rectifier devices. In chopper is a buck converter. So in a buck converter, you are having the single switch, single power electronic switch. So only you have to give the pulse to the single switch. So but here you can look at here, you are having this 6 switches here, 6 switches, so total 12 switches, here also 12 switches. So you need to give the 12 pulses to the converters, but here you have to give only one pulse because the single power electronic switch in the chopper. So the control wise it's very easy as compared to the top two topologies, right? So at the same time, if you look at it, if you connect any power converters at the grid terminals, it will inject the harmonics to your system, right? It will inject the harmonics to your system. For example, in our fan in our home, for fan control, we are using the triac. That triac itself injecting the lot of harmonics to the grid. So here also, if you are eliminating the converters directly connected to the grid, that we can able to reduce the harmonics to the grid. So because it's connected to the rotor of the machine. So rotor of the machine means it's not electrically connected, it's magnetically coupled. The machine also, just we are having the stator and rotor, so magnetically coupled, all right? So the harmonics injecting to the grid will be lesser in that case. The same way, and here in this topology, you can able to make this topology as a generator above synchronous speed. Above synchronous speed only it will act as a generator. But when we come into the WF induction generator, this will act as a generator even below synchronous speed. So here if I say my operating range is 1500 RPM to 1600 RPM means, in this case, in the WF induction generator topology, my speed of operation is 1400 RPM to 1600 RPM for 4-pole machine. I am talking about the 4-pole machine 50 Hz system, right? So my speed range is 1000. Here it's a 200 RPM. Here only you will get the 100 RPM. So for implementing the maximum power point tracking, if you are having the wide speed range means you can able to operate the machine at a low wind velocity as well as high wind velocity, right? So that you will get the wide speed range. So here you can look at here in that rotor, just we are having the back-to-back converter. Both are PWM rectifier. So again, you need to give the 12 pulses like earlier. But the advantage is the converter ratings are 30% because it will handle only the slip power, right? So if I say it's only 20% slip range means maximum you'll get the 20% of the stator power in the rotor winding. 10% you can say is overrated. So 30% of the converter ratings I can use it here. But in the top two topologies, I'm using the converter rating equal to the machine rating. But here the converter ratings are 30% of the machine rating. And you'll get the wide speed range. So this WF induction generator topology looks attractive for the higher capacity wind turbines. So once you know this basics of this wind turbine and the converters operation, then you can go with the different types of converters. For example, you can if you want to incorporate the battery energy storage in this WF induction generator, how will you incorporate the battery energy storage? Anyone having any idea? For example, I need this is for standalone application. I need to supply the standalone loads. So for that, I want to maintain the voltage frequency constant. So for that, for giving the energy balance and power balance, I need to integrate the battery energy storage. So how will you integrate the battery energy storage? Any idea? So what I can do is just I can put some power converters, and power converter means this is a charger, DC to DC converter. Then I connect my battery bank here. So why I'm putting this DC to DC converter here means, here if I say it's a 200 volt, the grid voltage is 415 volt. Obviously the DC link voltage is 600. So I cannot go with the 600 volt DC battery at the point and the DC link. So for that, what I can do is just I'm using some isolated converters. Then I can connect my battery in between the DC link. So only how I can do means once I know the basics of this power converters operation and the application characteristics, then I can go with the different topologies. So I think I'm running out of the time. So because of the limitation, just I stop at this point because I do not have a time to discuss with the various topologies. Even I have, and just we worked on various topologies and control strategies. Because of the time limitation, I stop at this point. If you have any clarification on this topic, please go ahead. Thank you. Any clarifications, any questions?
Participants have any questions or clarification, you can unmute and give and ask. Otherwise, you post your question in chat. Participants, if you have any queries, any questions, you can unmute and ask. Otherwise, we post questions in chat. Participants have any queries, you can raise.
I think they have exhausted.
Sir.
Sir, one question.
Yeah,
sir.
please.
Ashish Kumar.
Ashish. Proceed, sir.
So what will be the effect of blade geometry and aerofoil on energy generation? Yeah. So when we look at the wind energy conversion system, just we are having the choice to work on the electrical engineering perspective or mechanical engineering perspective. In again the mechanical engineering perspective, again just we are having the choice to work on the different materials for the wind turbines, especially on the blades. Even I told you the blades itself having the 15 to 20% of the cost. So in that 15 to 20% of the cost, even if the blades are robust, it's okay. But sometimes blades have broken, and I mean, even you have to spend the 20% of the cost for the repairing and all. So that's what people, they have come up with various types of materials, even different fibers and everything. In that case, you can go with different types of materials to enhance the aerodynamics of the system. That's what people are working. But I do not have deeper knowledge on that perspective, materials and the aerodynamic side. So, but you are having the scope to explore a lot of things on the blade side.
Thank you, sir. Another question asked by Ashish Kumar.
Is vertical turbine more effective than horizontal one? So normally it's a vertical axis wind turbine. Earlier days, if we have seen, they are used for the mechanical purpose, for grinding and all. So that will give the higher torque. But the stability point of view, the horizontal axis wind turbines are best one. So that's what they have moved from vertical axis to horizontal axis wind turbines. For small, I mean, we can say for a small capacity, yeah, you can go ahead with the vertical axis wind turbine. But for larger capacity, the horizontal axis wind turbines are the best candidate.
Thank you, sir.
Okay.
One more question will be asked by Vijayalakshmi. Instead of fixed blade, can be make blade to move according to its own axis of pitch angle. Means varying pitch angle can be we provide.
See, number of blades. I think I skipped that one. How they have arrived with the 3-blade system. You cannot change the number of blades, but you can able to change the pitch angle of the turbine. The pitch angle of the turbine means just we are tilting the angle of the individual blades. So just what we are doing is just we are tilting the angle of the blades, like in your fan. No, if you look at it, the blades are tilted. That tilting angle you can change it in the wind turbine. Why? Because on the every wing of the wind turbine having the motor. So by using the motor, you can able to change the tilt angle of the blades. So that we can, I mean, if you are changing the tilt angle of the blade, you can able to change the pitch angle of the blade. So once you are changing the pitch angle, then the speed of the wind turbine will change, right? So that once the speed of the wind turbine changes, then you can able to control the speed of the turbine. Okay, this is the in terms of pitch angle. Pitch angle you can change anytime, you can change by, because in each and every blade you are having the motors. So even nowadays, earlier they have the control, I mean they have changed the angle of the blade simultaneously. Now each and every motor having their own control. So one blade you can make it one angle like 18 degree, another blade you can make it 16 degree, because they now in modern wind turbines they are coming up with the individual motors in the blades. Okay, one point is that one. So when we coming to the number of blades, yes please.
So my doubt is, instead of providing a vane for the hub, can we make the changes in blades itself, sir? The blade can tilt as if the thrust of the air comes like that, it should change.
But you have to, I mean, yeah, for a small system, that's what I'm saying, no? For 100 watt, 200 watt, people are now, they are working. For that, we can do this kind of experiments. When we come into the commercialization, because these wind turbines are located in the remote location, no? So we cannot put more technologies on it. So if you are putting more, even frankly speaking, the 2005, in a actually I am from Coimbatore. In a Coimbatore, just we are having the lot of wind turbine players, right? So earlier for fixed speed wind turbine, they have given the soft starters to start the wind turbine. So because of the skilled manpower shortage, even they have bypassed that soft starter also. Why? Because they, I mean, sometimes they may get some interruption because of the soft starter. So that's what they eliminated. So even, but nowadays we are getting some skilled manpower. Even variable speed wind turbines also it's available. So for operating that variable speed wind turbines, we need the skilled manpower. So again, if you are putting a more technology in that system, again you have to upgrade the skills of the manpower, and they have to know the what are the fault that happened in it. Just I'm talking in terms of operational perspective. So these are also very huge O&M problems. So that's what people, I mean, for small system, obviously you can go ahead with that and you can play around with it. But for commercial wind turbines, they won't prefer that much. Even it may take time to do it. Okay. Again, when we come into the number of blades also it's matter. Why they have arrived with 3 number blades means, again it's a trade-off between your system cost as well as the operational speed. If you are going with the 3 number of blades, the system speed, I mean wind turbine speed will be less as compared to 2 blades or single blade system. Again, if people may ask, why not 4 and 5? If you are going 4 and 5, each blade cost also it's huge. So if you are going number of blades more, then the system costs will increase, right? Then if you are going with a less number of blades, the speed of the wind turbine will increase. So if the speed of the wind turbine increases, then again you will get the mechanical stability issues. And why it's a odd number of, I mean, even if you can see in a wind turbine, they will use odd number of blades instead of even number of blades. So for example, if you take the two blade system, two blade wind turbine, in a two blade at one particular point of time, you are having one blade on top and one blade on the bottom. So the bottom blade on the back side of your tower and the top blade on the free space. So the top blade will face the higher wind velocity, then the bottom blade will face the lower wind velocity. Why? Because that bottom blade on the back side of your tower, so that you'll get the shading effect. So because of that, it will face the lesser wind velocity. So top one higher wind velocity, lower one low wind velocity. So what will happen? Just there is a stability issues, so that it will affect the aerodynamics. Again, just that will deteriorate your efficiency of your turbine, right? So that's what they will prefer the three blade systems.
Thank you.
Yes. Yeah.
Thank you, sir. Almost we near to end of the session. I will thank our chief guest today's session, Dr. Vijaykumar. It's a very great presentation, sir. You focus the topics on energy towards wind and PV system and wind energy conversions and power electronics converters and modern power electronics components and various speed drives, and also we covered the power electronics controllers for wind energy system towards to the green energy technology. This is a very apt to this FDP, sir. It is very useful for current researcher and PhD scholars. On behalf of our coordinators, once again I thank you, sir.
Yeah, thank you.
You answered the questions. Okay, thank you, sir. You accepting our invitation and accepting to present this session, sir. Thank you, sir.
Okay, thank you a lot, and thanks for the invitation too. I hope the participants have enjoyed the session. So if they are having any further questions or any doubts, they can write it to me. So I'll be happy to answer their questions. If I have taken much time, so sorry for it. I think I have my time is till 1:10, but now it's 1:20.
Okay.
Thank you very much.
Thank you, sir. Thank you so much.
Thank you, sir. Thank you so much, sir.
Yeah, thank you, ma'am.
Thank you. Thank you so much.
Thank you, sir.
No,
Thank you, sir.
So shall I leave now?
Yeah, sir. You can.
Yeah, sure. Yeah, sure. Thank you. Thank you.
Dear participants, the next session will start at 2:30 p.m. I request the participants to join the meeting at 2:30 p.m. today. We have posted the feedback link in the chat box. Kindly give your feedback for this session. Thank you.